Okay, good afternoon, everyone, to this third session of the EU for Agriculture Under Pressure conference. This third session will be about the water resource management and productivity. We have about 5 different presentations. Each presentation will last approximately 15 minutes, and there will be a 5-minute time for discussion and question and answer. And if you have any questions to any of the presentations, you can always put them into the chat from beforehand already. We get them, we collect them. I'm convening this session together with Jippe from the FAL in Rome. And I would also like to mention that after this session, we have a virtual requirement platform, which is a chat discussion where we collect user requirements or requirements from scientists on agriculture and resource conservation. So please also tune in after this session, after the regular session, to join this event. First, I would like to introduce Livia Peiser from FAO, and she will talk on the understanding pressures through water lenses, the impact of conflicts and climate extremes on food and water security, analyzed with the FAO VaPOR portal. So Lydia, the floor is yours.
Thank you. I will be sharing screen. Okay. So thank you. I will be talking about the work we do at FAO in terms of monitoring water productivity in agriculture, and how this can be used to better understand pressures on the agricultural systems. And this is what I will be talking about is the results of a collaborative effort of several colleagues, which you see there. Their name is there. And of course, well, when we prepared the submission to this conference, agricultural systems were already facing unprecedented challenges. The number of undernourished people in the world was already at 690 million people, according to latest FAO publication. And much of the recent increase in food insecurity can be attributed to conflicts and climate-related shocks. We were also very much concerned of the increasing level of water scarcity in many parts of the world, and aware that agriculture is partly responsible for this, as it's the main water user globally. But of course, in addition to being responsible, is also part of the solution, because water helps making agricultural systems resilient to climate extremes. So that was already the type of pressures that we were looking at. But then, of course, suddenly a major pressure came into the picture. And now with the COVID-19 pandemic, FAO and other UN organizations have estimated that an additional 80 to 130 million people could be added to the total number of undernourished population in the world, depending, of course, on the economic growth scenario. And this is happening not only indirectly through the economic crisis, but also more directly through, of course, disruption of food value chains or limitations to workforce in agriculture. And water is again central in this. First of all, because of course water is at the forefront of the fight against the pandemic, and still we need to remember that around 3 billion people still lack basic hand washing facilities in the world. So this is telling us more and more that water is central to all these, central to these challenges, and we need to make sure that we use it well. And we need to use it well, particularly in agriculture, because, as we said, agriculture is the sector that uses most of it, that it's responsible for the largest share of withdrawals. And so we need to find ways to produce more food with less water, and remote sensing can help us a lot in this sense, And we have developed a system that helps monitoring water productivity in terms of measuring the output in kilograms per hectare per unit of water that is consumed to produce that hectare. That's what to produce that yield. And that is what we call water productivity, which is increasingly referred to in the international agenda. To do that, we developed the FAO together with international partners, a system that monitors key water-related variables, water and agriculture, of course, related variables like biomass, actual and reference evapotranspiration, precipitation, and so on, and translate them into assessment of water productivity. And we also use that for water accounting studies. We produce this data at different levels of resolution that also correspond to different types of inputs in terms of satellite sensors. We currently cover Africa and the Near East at 250-meter resolution. We have a number of countries and river basins that we cover at 100-meter resolution using what when we started it, we were using Probst as optical input in that, and a few 8 high-resolution areas where we provide data 30-meter resolutions at the moment. When we started this back in 2015, of course, the availability of Sentinel data was not operational. I mean, we couldn't build a methodology on that, but we are now further integrating more and more of Copernicus product into that. But I will come back to this point later. I just would like to show how this looks like in reality. We have a portal that's WaPOR, where we publish this data that comes every 10 days since 2009 to date on biomass development, water consumption, that is actual evapotranspiration, and in addition to other agroclimatic parameters like reference ET and precipitation or land cover. And we have that, as I said, at different levels of resolution. This is the continental level, this is the 100-meter level, and this is an area in Sudan, in the Gezira scheme. That we use to show that at 100-meter resolution you can already see a lot of spatial variability in an irrigation system, and you can already spot some tail and dynamics and see areas that need improvement or compare. For example, there's an area where the green is greener on the right part of the map, and that means that in those fields at least 1 kilogram of biomass is produced, even 2 kilograms for each cubic meter of water consumed, and that happens to be a more recent commercial farm that then can tell us something on how maybe other areas of the scheme could be improved in the way they manage water. Then we have the 30-meter resolution data. This is an area in Lebanon. And at this level, we already start seeing, of course, not only the big fields, but also the smaller fields, and that helps us coming up with targeted advices. And at this level, we also do crop mapping for this specific area, so we can develop together with the local counterparts specific crop-specific advices and policy recommendations. This is the diagram of the data flow and what's the input and output data. And this is all clearly explained in the methodology document that I will refer to in a minute. Just want to mention that the evapotranspiration is based on energy balance calculation, and particularly on a slightly modified version of ET-look, and the biomass is based on light use efficiency model. The methodology and all the algorithms are published and are available on the website. And all the data and metadata are available also through APIs, which make it easier to integrate into existing platforms or applications, including smartphone applications, for example. But I will just now quickly mention a couple of examples of how this is being used. This is one area in Mali. That's an area that is unfortunately difficult to visit these days. So that's a typical example where remote sensing can help. And with this information, we can help the scheme managers to assess the amount of water that is being consumed for growing, in this case, for example, sugarcane in the lower part of the picture that you see. That's it's a private company growing sugarcane, and they need to know how much water is being consumed for this exercise, and be able to plan the water allocation in the system. But the other example I wanted to make is again a similar type of pressure that's again a conflict related. This is in Syria, where we've been supporting the FAO office in their assessment of the damages to the irrigation sector linked to the conflict. In Syria, irrigation is supporting around 23% of the cultivated area, but unfortunately, starting from 2011, there has been a severe reduction in the agricultural production, with a record low in 2016, with about 40% of reduction compared to pre-conflict times. So we tried to see how we could help in this damage assessment, and look in using vapor data to understand the impact in terms of also quantifying and spatially identifying areas of where this damage was more felt. And so we looked at in particular, now I'm showing two examples. One is in the lower east part, a very dry area, but it's an irrigation area that is along the river Euphrates, and it's been, if you look at the total change in yearly actual evapotranspiration, it's been constantly decreasing, but you see variations, and you even see areas of what looks like an improvement, but then this is an example that shows that local knowledge and expert knowledge is still required to make sense of what Earth observation is telling us, because what seems to be an improvement, an increase in actual evapotranspiration, can be in reality linked to spreading to grass growing along the river, or weeds in the cropland area, or in some cases it can be linked to farmers using shallow wells that are not sustainable because of the salinity of the water in the area. So you still need to be able to interpret the results of the remote sensing analysis with the help of local knowledge, of course. Another area we've been looking at is more in the northern west part, near to Aleppo, and that's an area where the FAO has been supporting also the rehabilitation of pumping stations. In particular, what you see there is Sector 7. That indeed shows a very positive trend starting from 2017. So this kind of information, in this case, can help us monitor also the impact of the investments, of the work that FAO and other counterparts are carrying out in the country. But as I said, it is very important to have to interpret the remote sensing assessment with local knowledge, and that's why we've been working with the FAO office in Syria to provide capacity development for Syrian experts to use the data to interpret and come up with the analysis. And this we're very happy to. I've been able to do this also. Regardless of the difficulties and the possibility of traveling, but so that it's been an interesting exercise, and there's a lot of now capacity there to be able to use this data for improved assessment of this. As I said, the information. Yeah, thank you. I'm almost done. Because the information is available through APIs, it can be used and directly, let's say, plugged into existing or new applications. So for example, for providing advisory services to farmers on irrigation timing and quantities. We are also, of course, very much aware of the importance of having a continuous quality assessment of the data. So we've been, there was already a quality assessment on the version 1 of VaPOR, and another quality assessment of version 2 is now being finalized and will be online soon. And in addition to that, there are also a number of independent papers and research papers that try to look at the accuracy and also the use of this information. I'll just close by mentioning how we see the future. So we want to grow, of course, to extend our database in time and space. And as I said, we are now looking into stronger integration of Copernicus products in our data. We already use Copernicus products for the land cover. We use the global land cover product, and we use we've been using Probst and now using Sentinel for the level 2 calculations. But we want to go further, and thanks also to a collaboration with the European Space Agency, there's a spin-off activity of the SANET project that is now looking at translating, let's say, the methodology developed for evapotranspiration in VaPOR, translating that with more of Sentinel inputs in the ET algorithm. So we're very we are looking forward to the results of this study, and because we are very much aware of the fact that the Sentinel can help us improve the temporal and spatial accuracy of the data. But another thing we really look forward to is the implementation of the land surface temperature monitoring mission, because to have good data on evapotranspiration, you need, using a surface energy balance, of course, the land surface temperature is a key input data, and at the moment there's no valid, let's say, product in that sense, and we really hope that Copernicus will fill that gap. And we're looking forward to that, because we are sure that it will be a game changer in this data. With that, I will conclude and leave some coordinates on how to reach us. Thank you.
Okay, thank you, Livia. I see there are a few questions. The first question is to Livia. Can this be done for all Syria in more detail, using higher resolution to identify damage and list priority for the irrigation rehabilitation schemes? That's one question. And another question that comes from Sudan: are you testing your methodologies in rain-fed systems, because the irrigation systems and irrigation scheme is almost controlled?
Yeah, thanks. That's two interesting questions. The first one on Syria, yes, this could be done. That's why I think it's important to invest on the capacity development of the Syrian experts, because it's only with them that we can really identify what priorities are there. And if high resolution data sets is a priority, then we can work on that and see how this could be done. We are one of the idea we have. I mean, as I said, the algorithms for calculating vapor data are freely available, but it's not so easy to run them. But the idea is to be able to develop capacities in that sense as well, so that when a need is recognized, there's also local expertise ready to implement this type of analysis. And as for the second question, yes, we do. Well, as you could see on the map, the database covers both irrigated and rain-fed areas. It covers the whole area at a continental or national level. There's also examples of using this in rain-fed systems. For example, in Ethiopia, you can see on our website there's a pilot study done in an irrigation system, but also in the rain-fed season, and see how water productivity monitoring can help also coming up with recommendations for improving water productivity under rain-fed conditions. So yes, we don't have that in Sudan in particular, but in neighboring countries we do.
Okay, thank you very much, Livia. Let's then go quickly to our next speaker, which is Rado Guzinski. He was more or less already introduced by you, Livia, in the sense that he's going to tell us a little bit on how to model actual evapotranspiration at field scale through Sentinel-2 and Sentinel-3 data fusion. Go ahead, Rado.
Yes, thank you, and good afternoon. Let me just share the presentation. And just have to switch the screens, and I'm ready. Okay, so yes, thank you for the introduction. My name is Rado Guzinski. I work for a company called GRAS in Denmark, and in this presentation I'll be showing it's based on work performed in the Sanity project, which Livia also briefly mentioned in her last slide, and it was performed together with the partners listed here. And the aim of the Sanity project was to model actual evapotranspiration at field scale, so at high spatial resolution, and to do this using Sentinel data, especially Sentinel-2 and Sentinel-3. So firstly, a short introduction for why there is a need for mapping evapotranspiration. There is a lot of pressure on the global freshwater resources these days, with the growing population, also growing economy and consumption. And worldwide, it's estimated that around 70% of the freshwater withdrawals are used in agriculture. In Europe, that number is a bit lower, 40% on average, but in Southern Europe, it also reaches around 70%. And the main use of water in agriculture is for irrigating crops. Because of this, there is legislation, national or international, at different levels for preserving water. So, for example, in Europe, there's the European Green Deal, which mentions water conservation. The Common Agricultural Policy also has a component on that, and there's the Water Directive. On the global level, there are the Sustainable Development Goals, and particularly relevant is the SDG 641, which is changing water use efficiency over time. And actual evapotranspiration is almost direct proxy of irrigation water use, because it tells us the amount of water transferred from the surface into the atmosphere. So by knowing this actual evapotranspiration, we can firstly monitor water use in irrigation and hopefully improve the efficiency of the use of this water. Thankfully, as well, we have a lot of data which is suitable for the purposes of monitoring evapotranspiration with Earth observation. If we look at the Sentinel satellites as a constellation, it is highly suitable for agricultural monitoring. So firstly, it has both optical and thermal infrared observations, both of which are critical for modeling actual evapotranspiration. Also, it has a high spatial resolution, so we have the 10 and 20 meter spatial resolution of Sentinel-2, and there is high temporal resolution as well, because Sentinel-3 has up to daily revisit time. There's other Copernicus data as well, which is highly relevant for modeling evapotranspiration. For example, meteorology from Copernicus Climate Data Store, so the ECMWF models, and there are ancillary data such as land cover maps from Copernicus Land Monitoring Service. And here I briefly put on my other hat, because apart from developing ET, I'm also working part-time as a consultant at the European Environment Agency. So I would like to highlight some of the products they produce, which are relevant for ET modeling. I already mentioned the land cover, for example, Corine. We already used it in our ET models. Currently in development is Corine Land Cover Plus, which is an update of the Corine, so be more dynamic, updated more frequently and contain more information. There's also a high resolution layer called crop types, which will be produced soon. And by knowing the different crop types, we can again parameterize the models better to get more accurate estimates. And there are other products, like, for example, vegetation phenology and productivity, which could be combined with the actual ET estimates to estimate water use efficiency. Now, going back to the Sentinel data, as I said, as a constellation, the system is highly suitable, but there's a problem that there's a lack of high-resolution thermal data. So here we have a Sentinel-2 image and Sentinel-3 thermal image covering the same area. And in the Sentinel-3 land surface temperature, obviously we cannot see any of the landscape features because it's captured at 1 kilometer spatial resolution. So in the Sanity project, we performed developed a method to fuse the two data sets to get a high resolution representation of the land surface temperature. The fusion approach is based on machine learning. In this case, we used a bagging ensemble of modified decision trees. And basically, it works on the principle that first the high resolution data, so the optical Sentinel-2 reflectance is resampled to the lower resolution. Then you build the model, so the relationship between the optical data and the thermal data. And then you apply the same model to the original high resolution optical data to derive the representation of land surface temperature at the high resolution. This method works on pairs of optical and thermal images, and they can be up to 10 days apart without too much loss of quality, which means you can obtain quite dense time series because you can use multiple Sentinel-3 images with one Sentinel-2 image. And the main assumptions in this data fusion approach are that the relation exists between optical and thermal images. So this relation does exist localized in space and time, so basically in those two pairs of images. For example, in the optical data of Sentinel-2, we have the shortwave infrared bands, which tell us something about the water content in the pixel, and the more water, the lower the temperature. But there are also red edge bands, which tell us something about photosynthesis and chlorophyll, and as well the higher the photosynthesis rate, the lower the temperature, and other such relations do exist. However, this cannot be generalized, so there's no one model that will fit globally, so it has to be trained on the pair of the images. And the second assumption is that this relation is scale independent, so when the model is trained at the lower resolution, it can be applied at the higher resolution. And once we have this representation of land surface temperature at high resolution, we use it in the evapotranspiration model. we use the two-source energy balance model, which is a physical model. It models the land surface energy fluxes, including the latent heat flux, which is the energy used in evapotranspiration. And the two-source energy balance model can internally partitions the evapotranspiration into evaporation from the soil and transpiration from the vegetation. So we get those two components. It's also robust in many environments because it's physically based, and as well it's been developed for many years and is continuously being developed further. And once we get this land surface energy fluxes in watts per meter square, we can extrapolate them to daily evapotranspiration in millimeters per day. So the results from this method were validated against 11 flux tower sites. They are presented here on this map. You can see that they were spread over different land cover types and as well across different climates. And when running the model for the validation, we used only global data sets, so global land cover, global meteorological data, and the global satellite data, obviously. So, and no site-specific parameterization was used. So in the table here, you can see the main statistics as related to the latent heat flux. So overall, again, across the 11 flux tower sites, we get relative mean square error of 0.45 and correlation of 0.6. If we look at cropland specifically, the error decreases and it approaches the range of uncertainty in the flux tower measurements themselves. And here's a reference to the paper where the methodology is described in more detail and the validation as well. So once we had the method validated and developed, we coded it as an open source software and released it as a plugin to the Snap software, which is supported by ESA. The software provides end-to-end processing. So here you see one part of the modeling flow, just to show that this is quite extensive and complex. But it basically starts from downloading the Sentinel-2 and Sentinel-3 data and ends with daily evapotranspiration maps. And this is all done through the Snap user interface, so there's a graphical user interface. The plugin can be downloaded from the website shown here, and as well there's a community support on the Snap forum. So now I will show a couple of applications of why high spatial and temporal resolution evapotranspiration is needed. So here I hope you can see the video, but basically it shows the first type of application, which is monitoring of water use. This is for water rights monitoring, for example, to make sure that the users of water don't use more than they are allowed. And first we can see that at 1 kilometer spatial resolution, we do not see the details, and on this plot, the black line shows the evapotranspiration over the season at low spatial resolution. And we can see that it underestimates the evapotranspiration modeled in the two circular plots when they are modeled at high temporal resolution. And secondly, we also miss the temporal dynamics of the evapotranspiration and the water use in those two plots if we look just at the low spatial resolution. Second application is using this information for Sustainable Development Goals reporting, especially the 641, which is the water use efficiency. We conducted a pilot study in Uganda where we monitored evapotranspiration in all the major irrigation schemes in Uganda. And we compared the evapotranspiration within the irrigation scheme to evapotranspiration of an agricultural area close to the scheme but not being irrigated. And as you can see here, this irrigation scheme, even though it's considered a large scale or medium scale, and it's still only a couple kilometers across, so with 1 kilometer land surface temperature data, we would not be able to capture or to differentiate the irrigated and non-irrigated areas. And on the plot at the bottom, you can see the yellow dots are the water use during the dry seasons. And then as well, we took the biomass production from the WaPOR portal of FAO. And from this, we can see how the productivity of the or the crop water productivity, so how much biomass was produced for a cubic meter of extra added irrigation water. Another application is irrigation advice. Again, here we have to, it is important to have this data at high spatial and temporal resolution to give the advice to the farmers on their field, and possibly even to observe the within field variability. So here is an example of one such product. So it's based on the difference of the actual and potential ET. And we can derive, for example, crop water stress index, which is a normalized index, where 0 is well water vegetation and 1 is severely stressed vegetation, or we can provide water deficit maps in millimeters. And such information can be used by the farmer to better plan allocation of their water and equipment, because often they have to move the pumps around or the irrigation equipment around to different fields. If they know which fields are more stressed, they can better plan this. And possibly
another 2 minutes, please, Rado.
Yes, I'm getting close. Possibly it can also be used for variable irrigation, so kind of precision agriculture, which brings me to the next slide, which was another study done by some of the project partners from CENITI, where they assessed the use of the CENITI method for precision irrigation, so deficit irrigation in vineyards, and they compared the information obtained from the CENITI method with information obtained from high-resolution airborne data. And the result was that obviously the airborne data is more accurate because the sharpening itself, during the sharpening, you don't gain as much information as if you had the high resolution data originally. For example, you miss the extremes in the temperature. As well, the sharpening uses the optical data, so if the information is not in the optical data, it will not be observed in the sharpened LST. So using this LST for things such as precision agriculture is pushing the limit of this approach. And this brings me to the last slide, which is that the lack of high spatial temporal thermal data is still an issue. So with the CENITI method and this kind of data fusion of Sentinel-2 and Sentinel-3, we can do a lot, but we cannot do as much as if we had the actual high spatial temporal thermal data. And thankfully, the LSTM, which is the Copernicus Land Surface Temperature Monitoring Mission, is one of the Copernicus high priority candidates. So it is being evaluated, and different studies are being conducted on the feasibility of such mission and on the requirements. And here are highlighted some of those requirements. So basically, to be up to daily and 30 to 50 meters with high accuracy of the thermal data. So, like Livia mentioned, once this mission is up and flying, this will be a real game changer in modern monitoring evapotranspiration globally at high spatial temporal resolution. And with this, I would like to thank you and ask for questions.
Yeah, thank you very much, Rado. I see there is one question from David Rias, but he says, I believe this is maybe better for the panel discussion in the end, but maybe you can answer it right away.
Okay.
He asks, there are a lot of, there's coming in something from, okay, that's another question. So this question is, there are lots of clusters of, well, I guess it's intense water use on the greenhouses. Is it possible to estimate with Earth's observation evapotranspiration from these schemes, so from greenhouses?
I think it will be quite difficult. I mean, the greenhouses obviously change the reflectance properties, so we cannot see the state of the vegetation itself. The thermal data as well is changed. So yeah, I think it will be quite difficult. It would require its own research projects to check the feasibility of monitoring ET from greenhouses.
Mm-hmm. Okay, and there's one more question, and maybe that's even more addressed to Isa, because it says SEN-UT gets land surface temperature data through Copernicus Hub, but these data are only readily available for the past year. How to properly process other years in SNAP?
Maybe it is better for Isa to answer, but as far as I know, the LST is available since the beginning of Sentinel-3 mission. I saw that Sentinel-3B land surface temperature is being reprocessed right now and should be released soon. And I think Sentinel-3A land surface temperature product also goes back to the beginning of the mission. So it should be since 2017, I think it was.
Okay. And maybe I have one question for myself before continuing, because there are no other questions left. You're discussing Sentinel-2 and 3, but have you ever thought of including fluorescence? So currently from Sentinel-5P, which is of course very poor scale, but maybe in the future also flex.
Yes, I mean, in general, the more data you input, the better it is. We are thinking about, at the moment, using soil moisture from Sentinel-1 as well, in combination with the evapotranspiration from Sentinel-2 and 3. In different biophysical models, the fluorescence could also be of use. So again, this is something that will have to be researched. The method as it is right now cannot easily incorporate such new information.
Good. There are more questions coming in, but I would like to save them for the discussions as session in the end. With this, I would like to continue with Elisabeth Probst from the Ludwig-Maximilians-University in Munich. And the title is Coupling Agro-Ecological Modeling and Sentinel-2 Observations to Measure the Water Use Efficiency of Crop Production. The case of agriculture in Romania. Please, floor is yours.
Thank you. I'm just sharing my screen. So thank you and good afternoon. My name is Elisabeth Probst, and it's my pleasure today to present you our current research on coupling Sentinel data with crop modeling. The topic is coupling agro-ecological modeling and Sentinel-2 observations to measure the water use efficiency of crop production. The case of agriculture in Romania, so we conduct this in a case study in Romania. And to provide a little background, the major focus of the UN Sustainable Development Goals is on water-intensive sectors such as agriculture. So when we think about rising global crop yields for food security, we must also ensure that water resources are used in the most efficient and sustainable way. So improving water use efficiency is key for sustainable agricultural management. As we have already heard before, water use efficiency is defined as the ratio between crop yield in kilogram and evapotranspiration water in cubic meter of the crop in the whole vegetation period. We are working in the VIVA project, where we aim to develop a global high-resolution monitoring system for observing agricultural management and for assessing sustainability of agricultural water use. The core is now a coupling of GOMET crop simulations with Sentinel-2 Earth observation data, which makes it possible to derive actual management, yield, and water use efficiency. Our study region for this is the Romanian plain. It is located in the south of Romania, as shown in the map below, where you can see the border of the Romanian plain itself in blue, and the respective counties in black, which hold a share of the Romanian plain. The plain is an extensively used fertile cropland with large agricultural potentials, but recurrent droughts appear here. This region also features low crop yields and water use efficiencies due to poor fertilization, also a low degree of mechanization, and also inefficient irrigation. What we like to find out is now what is the actual state of agricultural management, yield and water use efficiency for example, winter wheat. Now our approach is based on a coupling of the PROMET crop model with Sentinel-2 satellite data. For an overview, PROMET is an agro-ecological model which performs biophysically based crop growth modeling. It is spatially explicit and works on a custom spatial resolution. In the study, we chose 1 square kilometer as resolution. It models on hourly time steps and also allows the assimilation of Earth observation data. PROMET is driven here by the global reanalysis dataset error 5 and requires gridded input data on topography, soil, and land use, for which we used here the SRTM, the Harmonized World Soil Database, and also Foreign Land Cover 2018. Plus a set of parametrizations describe the physical processes of vegetation and soil, and also agricultural management parameters are required for the crop modeling, which are unknown beforehand and which we have to find out. I will go into more detail on this on the next slides. So the output of the simulations is actual winter wheat yield and water use efficiency for the year 2018. And we validated yield by yield statistics on county level. And now to have a link to, let's say, reality, PROMET also allows the assimilation of LAI data, which means that the model LAI is updated by external data streams. In this case, we use the LAI courses from Sentinel-2 images. Now, the question is now, how do we derive LAI data from Sentinel-2 images? I will tackle this very short because this is work done by our project partner Vista, and there is another talk held by Silke Migdal, I think on Thursday, tomorrow, which goes into more detail on this. In short, there are 21 tiles covering the Romanian plain, and we processed all of them for the full growing season of winter wheat in 2018. Now, the Sentinel-2 processing chain includes some pre-processing steps, namely atmospheric correction and also crop type classification. And the crop type classification identifies pixels on which winter wheat was grown in 2018. Then, by the help of the radiative transfer model SLC, the green LAI is retrieved for all pixels. And afterwards, a representative sample is drawn from the pixels, and finally a temporal interpolation is done for the sample to get continuous LAI courses out of the discrete values for each winter wheat pixel. Finally, the output is a sample of over 10,000 pixels identified as winter wheat in 2018, for which LAI courses are available. Now we go for the modeling. The first step now is to inform PROMET with Sentinel-2 to find out the actual management of winter wheat. To achieve this, we run an ensemble of PROMET simulations with a large variation in management. There's variation in different seeding dates from early to late, different fertilization levels from poor to high, and also different cultivar selections from early ripening to late ripening varieties. And this amounts to a PROMET ensemble with over 2,000 members. Now, the plot shows our procedure as an example at 1 pixel. We have first the Sentinel LAI course, and then many different LAI courses from the PROMET ensemble. And afterwards, we compare the Sentinel LAI to the different PROMET LAIs and select the best fitting ensemble member on every pixel for which the PROMET LAI shows the lowest RMSI comparison to the Sentinel LAI. The best fitting ensemble now has a very unique set of management parameters which we identify as also the best fitting management and the actual management for this pixel. So now have a look on the spatial results of actual management, the result of what we have learned from the ProMate Sentinel comparison. We see now the distribution of seeding dates on the left map, and apparently there's quite a variety of seeding dates. In the eastern part, derived seeding dates are very late in the year, and what we also know from local farmers is that here winter wheat is likely to suffer from frost damage over the winter and has often to be reseeded in early spring. On the right map, we see the distribution of fertilization level, which shows large differences likewise, most notably clear hotspots in the center of the map. Hotspot of poor nutrition status around Bucharest, apparently. Now, the second step is simulating Sentinel-2 and ProMate to find out actual yield and water use efficiency. Now, just a reminder, the best fitting ensemble member and thus the actual management is known on every pixel. So we perform a direct assimilation of the measured Sentinel-2 LAI courses in ProMate simulations, which are driven with the best fitting, which is actual management per pixel. We see ProMate is updated by Sentinel LAI and exactly matches its curve. So through the assimilation, we determine actual yield and water use efficiency for every pixel. And this is much more accurate with assimilation than without, because the modeled LAI development exactly matches to Sentinel. And this is why we include this extra step. So let's have a look on the maps of actual yield, which is in the middle, and water use efficiency on the right. The result of what we have learned from the assimilation. Winter wheat amounts to about 5.5 tons per hectare on average, and we see very clear spatial patterns between low-yielding areas in the center and in the northeast, and high-yielding areas in the southwest and also in the southeast. And these patterns, they can be traced back mainly to different fertilization levels and also to different water holding capacities of the soil, because in the south there is the Danube. This could be a very clear reason of it. We have also validated a simulated yield with statistics on county level from 2018. And what we see is quite a satisfying result with a slight overestimation by the model, as you can see from the trend line, which amounts to 1.3. But we get a quite strong correlation with R squared of 0.5. However, of course, we are still in the ongoing process to improve our selection process of the best ensemble member, and also of our filtering techniques and so on. So besides, water use efficiency of winter wheat amounts to 1.8 kilogram per cubic meter. And also here we see water use efficiency patterns, which are in very close relation to the spatial patterns of yield. So low yields are connected with low water use efficiencies, and high yields are connected with high water use efficiencies. And this makes also perfect sense, as high yields cause a higher water use through transpiration, but the share of unproductively evaporated water from the soil is getting less and less when lifting yields. So this is a strong indication for us that water use is rather unsustainable and also almost wasted in low-yielding areas. So to conclude, coupling data streams of high-resolution Earth observation satellites, for example, Sentinel-2 with mechanistic plot models, as we've shown it here with ProMate, results in a deeper understanding of agricultural practices. So we derived actual management through our Sentinel ProMed comparison and determined actual yield and water use efficiency through our assimilation runs. In the course of scenario studies, which we also conducted, we can identify yield gaps and unwell potentials to maximize water use efficiency. And this opens up the possibility to formulate tailored management recommendations for a more efficient and sustainable use of scarce agricultural water resources when lifting crop yields. And this is a very important thing in especially drought-prone areas where a special emphasis should be put on the improvement of water use efficiency rather than yield maximization. So for now, I'd like to thank you very much for listening, and I'm looking forward to your questions.
Okay, thank you very much, Elisabeth. We have a question from Amali, I think, and it says, if you define water use efficiency as yield evapotranspiration, how would you differentiate it from crop water productivity, which is also defined as yield over evapotranspiration?
Yeah, I've learned in the literature that there are many synonyms ongoing and also some differences in the ratio. So I think I would handle it as a synonym, but there are also some other ratios I know. For example, when you include the hectares, I think, or but I would tackle it as a synonym here.
Mm-hmm. Okay, thank you very much. There is another question, and it says it's from Wouter actually. He says management optimization can only be done after the season, so there is no time to react in the current season. Is there a way to use the tool in the current growing season?
This special tool, it is not possible to use it in the current growing season. It is made for recommendations to farmers which tend to not change their management over the years, but stick to their management routines which have worked out for them in the years before. But I think I can refer to Vista maybe on tomorrow's speech. Vista is actually doing all these things about yield forecasting and also recommendations on fertilization on demand, actually.
Okay. Thank you very much. Then I also have a question. You referred in the beginning of your presentation. You referred to the UN Sustainable Development Goals. How do you see that this can help the UN in reaching these goals?
Yeah, it is for ensuring food security in regions where water is very scarce, because it is better to know where, for example, irrigation water can be applied, or let's say it otherwise, you can apply irrigation water only once, and now it is better to apply it in regions where the outcome is better, there is more yield, and maybe to think about inefficient ways of irrigation, where water is rather wasted and where the yield outcome is not as good as it would be in more efficient regions.
Okay, thank you very much. Then there is no other question. So then I think we can go to the presentation. And the next presentation is from Nadja den Besten, who is working for VanderSat. And it is on analyzing the effect of basin-scale hydrology to field-scale water management with the help of different satellite products. So please go ahead, Nadja.
Thank you, Jippe, for the introduction. Is my screen visible? I think so.
Yes.
Yes, great. Yeah, so my name is Nadja den Besten, and as Jippe said, I work for VanderSat, and I'm also a PhD student at Delft University of Technology. And wait, I have to get rid of something here. And And the topic of what I will want to share with you today is analyzing the effect of basin-scale hydrology, specifically in catchment in Mozambique, and to also see what's happening on field-scale water management with the help of different satellite products. So going through different spatial resolutions. But before I start, how do I go to image? Oh, like this. Technology is still a very hard thing. But before I start, I would like to point out why irrigation and remote sensing, or why is it important that we as remote sensing scientists talk about irrigation. And it is, of course, to get insight in how much water is being used in irrigated agriculture and to really guide timely and efficient irrigation, ideally. And therefore also to increase the crop productivity, as too much or too little water negatively affects crop yield. And irrigation will increase in the near future, as it will go hand in hand with global population rise. And therefore we need to be extra careful with our freshwater resources, as was mentioned by prior speakers. And hopefully this presentation will also demonstrate the importance of that matter. So I would like to take you to the lower Inkomati in southern Mozambique. It's part of the Inkomati river system, and in this lower Inkomati there's a big dam called the Kurumana Dam. It's almost at the border with South Africa, next to the Kruger Park, actually. And in this dam, a lot of different users are making use of this Kurumana water dam. So it's a very important reservoir for a lot of stakeholders. And we looked at what is actually happening upstream in the average soil moisture of this catchment, where all the water is bundled in this reservoir of the Kurumana Dam. And then we looked at the average soil moisture, which is indicated over time here in the gray. And in blue you can see the average water level over time of this specific dam. And what is very interesting to see is that the lows in this water level and the soil moisture that is observed by ESA's SMOS soil moisture product. The average soil moisture in the catchment upstream of this dam links to what's happening in the water level of the dam. So there seems to be a time lag, and that can be very relevant to water management purposes. Also, if we look at the sort of heights in both of the time series, we see mean values here plotted in January of both the soil moisture in the catchment and the water levels in the Kurumana Dam. And there is a high relationship in those as well. So it seems that there is that the soil moisture we see from space is really indicative of the reservoir amount left. And that's useful, especially in such a drought-prone area as southern Mozambique, where water management is of utmost importance. So what we can also see in this time series is that from 2014 onwards, you see a decreasing trend in the soil moisture and also a decreasing trend in the water level of the Kurumana Dam. And then in 2017, you see that it's increasing a bit, but still there's a decreasing trend, and it's a bit worrisome. You see that the reservoir is basically depleting, what we can see from space as well, which is fascinating and worrisome at the same time. And this, this down or this decreasing trend has its effect on a lot of people in the lower Incomatic catchment. As from this year onwards, the Kurumana Dam will also provide Maputo, the capital of Mozambique, of water in times of drought. So actually, this period, a lot of water will go from the Kurumana Dam to the city of Maputo. So there's some conflicting interests here, where satellite data can be of use. Also, there are a few sugarcane plantations in this catchment, which are very irrigation intensive. However, it's also a large contributor to the regional employment. And then I want to go from this catchment scale problem to what's happening actually in one of those sugarcane plantations and what we can see from space. So I want to go from the Kurumana Dam to one of the sugarcane plantations in the lower Incomatic, and that's in Shinaban. And it's a big sugarcane plantation with 18,000 hectares of irrigated sugarcane that is irrigated throughout the year. And almost it uses 10 times as much water as the city of Maputo does in a year. So big numbers of water, but nobody really knows how much water because it's not really measured. But it's very important to know, of course, if you want to manage those resources in such a drought-prone catchment, to know what is the impact of such a plantation in order to make decisions on expansion or something else. And here evaporation can, of course, be key to see how much water is required and how much water is actually used. And within the work I've been doing with my colleagues, we looked at combining basically Sentinel-2 data and meteorological data to get to evaporation estimates for the plantation on a 20-meter resolution and get to daily estimates with the help of the meteorological data that was provided by the plantation on site. And then we used NDVI basically to look at the crop development of different fields and to distract crop factors over the specific fields that could be used to transform. In this case, a Priestley-Taylor formula was the basis for evaporation calculations to get to a maximum crop evaporation estimate. And then the second step basically was going from what is maximally required by the sugarcane to what is actually being used. And for this we used NDVI also as a stressor. We saw in the last crop stages of the sugarcane that the amount or the NDVI and especially the CV values of the NDVI were really linked to the yield performance category. So we use this as a means to get to actual evaporation estimates. And if you want to read more about that, you can go to this recently published article. And now I would like to zoom in to what if you apply such a methodology or any kind of methodology on such a small scale, a small temporal as well as spatial scale. So you're now looking at 5 sugarcane fields that give the difference between the maximum crop evaporation and the actual evaporation. So really deficit, really the stress is being portrayed here. So red means more stress, blue means less stress. And the numbers indicated in the fields are the yield over that specific growth season. And that's indicated in ton cane per hectares. And this, as you would expect, is that the two fields here that have a relatively lower yield also have more stress. And if we would use this in an irrigation context, we would say, okay, probably these stress are in such a drought-prone area, they must have had too little irrigation. But what's interesting is that actually waterlogging is the issue in these fields. So too much water is being applied, causing stress visible from space, or what we see through our calculations with satellite data, is now actually caused by too much water. And yeah, that's also mentioned here in this article. And it's this is not something that happens in one or two fields. It's happening throughout the plantation. So you see really areas affected by application or drainage, or basically waterlogged areas that link also to the low productivity areas. And well, with a large database from this plantation and also the yield information and information from different Earth observation sources, we're now trying to look at, okay, what is the spatial temporal variables, how are they affecting the yields in this particular plantation, and how much of this is contributed to drought, what we see on a catchment scale, or what other processes are behind this. So we are now looking at, for instance, the height above nearest drainage, which is calculated from the LiDAR information. We're looking at high resolution soil moisture products from VanderSat, and look at the water excess and the droughts on a field scale. We're looking at the temperature, soil type in all the over the whole database we have. So within all the fields and all the years that we have, we apply and we look at these spatial temporal variables. And then one of them is also ratoon. And ratoon is affecting the yield of sugarcane as well. And as you might know, sugarcane is harvested every year, but every 8 or so years it's replanted completely. But there's also natural decay in over the ratoon years. So if you go to the lower left figure, you see the average yield over the ratoon years, if you consider the whole sugarcane plantation, the yield database. And then you can see that there's a natural decay over the ratoon years. So in order to really do this spatial temporal assessment with all the variables identified, you need to consider this as well and basically cluster the effect of the ratoon. So then if you look at the change in yield per ratoon, what you see at the right figure, and especially look at the standard deviation in the right lower figure, you see that after 3 ratoon years it sort of stabilizes. So we choose now to do an analysis in categories for first ratoon year, second ratoon year, third ratoon year, and 4 to 8 ratoon years. And with this whole database and all the variables explained here, we are considering this database. And this is still work in progress, but I would like to share that the drainage and field leveling explains a lot of the variation in the data set if you look at the preliminary results in all ratoon and yield categories. And what is just very interesting is that on this considering this plantation, the poor performing fields, and looking specifically at the poor performing fields, soil water access is really an issue that is driven by field irregularity and also drainage issues, and probably also excess irrigation. And it seems to be that this variation in the spatial especially the spatial variation can be explained by waterlogging. And that's interesting because we're still talking about this same semi-arid and drought-prone environment that was described earlier. And to mention, satellite evaporation algorithms for irrigation also need to consider stress resulting from water access, even in these drought-prone areas. So some take-home messages from my side is that it's important to not only look at water use, but also really link to productivity, as many have done as well, looking at water productivity, also as a community to reach out to a larger group of people that speak more the language of monetary values or kilograms, that's something to be pointed out. Secondly, also the average catchment soil moisture withholds predictive information on reservoir storage that can be of use in managing water resources, as we saw at the start. And for irrigation purposes, evaporation or satellite-based evaporation estimates need to be related to drought only to prevent over-irrigation, basically. And at last, poor drainage and waterlogging seem to be the main productivity issue in this sugarcane plantation, despite the fact it lies in a semi-arid and drought-prone location. And with that, I would like to conclude, and thank you for your attention, and please share your thoughts and questions.
Yeah, thank you very much, Nadja. There are a couple of questions. The first one is from Sosdito from Mozambique, actually, and he says, or he or she says, very nice study, but did you also consider what is happening in South Africa? Because the Nkomati River flows from South Africa and the irrigation there is very intense.
Mm-hmm. I don't think I fully understand the question. Is it just a comment or is it a question?
No, it's a question because if you're looking at the water level as assumed, then you're looking at soil moisture, but not how the water in South Africa is being used and tapped by.
Yeah. No, we are looking at the relationship of the soil moisture and how that translates still to the Nkomati or the Korumana dam levels. So that's also still work in progress. But it's a good comment, though the catchment that we're now talking about, the Sabi catchment of this specific Korumana dam, really comes from also a natural, relatively speaking, natural environment, because it's largely coming from the Kruger Park.
Thank you. The next question is, could you please explain a bit more on how Sentinel-2 metadata are used for the calculation of water use on the fields? Sorry. I repeat, because it was shipped, the screen was shipped. Could you please explain a bit more on how Sentinel-2 metadata are used for calculation of water demand and usage?
I missed your publication slide. Okay, well then, I will shortly explain it, but it's a bit, I think, too long to explain it in full. So please Google then Besten evaporation and you will get a link, and then you can read it. But we use Sentinel-2 to calculate albedo and also NDVI that is used to get crop factors, and we use NDVI also as a sort of stressor to get to actual evaporation. That's in a nutshell what we're doing.
Mm-hmm. Okay. And one final question before we move on from Maria Suarez. What is the spatial resolution that you have used for the computation of water used on the fields? And what kind of meteorological data did you use?
Yeah, so the resolution is spatially 20 meters. And the meteorological data used, there are two meteorological towers at the plantation itself, so the data was used as an input as well. That helped in getting to daily estimates.
Mm-hmm. Okay, thank you.
Thank you.
Yeah, thank you. Thank you too. Before moving to the last presentation, I would just like to remind the people online also that there will be a virtual requirement platform session after this session. There will be a chat where you can ask any questions or make propositions, proposals on any mission concepts that are needed. There will be a 1-hour chat discussion following this one, and you can access this through Brella. For the questions that were not answered on the specific presentations, because of the lack of time, there are remaining 20 minutes after last presentation to discuss these issues and questions. So the last presentation will be given by Felix Rempel from Joint Research Center, titled Field Level Agricultural Monitoring Anywhere on the Globe with the ASAP High Resolution View.
Thank you, Chair, and good afternoon, everybody. Well, the subtitle of this session was actually Irrigation, Drought Monitoring and Early Warning. So I think we have seen excellent stuff about irrigation, great applications about water use efficiency modeling. With this presentation, I would like to move a little bit more into the second part, operational drought monitoring and early warning. And the presentation is about a system, an early warning system that we developed at the Joint Research Center of the European Commission to monitor crops all around the world, especially in food insecure areas and with different resolutions by using satellite imagery and also weather data. One point I would like to make with this presentation is also that we have now, since 5 years more or less, these great satellite images from the Sentinels that we have seen in all presentations, Sentinel-1, Sentinel-2, Sentinel-3. But what I think is also very, very important is that we continue the development of information platforms that allow to access, to visualize, and to integrate those satellite imagery into monitoring systems so that we allow to the better use of these images also to non-Earth observation experts who can access them and visualize them without programming skills. And to lure you into this thinking, into this presentation, I selected this beautiful image of an area in Sudan, in Sennar State, which is experiencing severe flooding since a couple of weeks. You can see that many fields are submerged. And this is just to make the point that if we can easily retrieve and access satellite imagery quickly in a question of seconds anywhere on the globe, we can zoom down to the field level and look for such things like water covering fields for irrigation or for flooding. Now, in this audience, I think I will probably not need to repeat very often that climate extremes and climate variability remain one of the major two drivers of food crisis, together with conflicts. And due to this, we continue to need improved early warning information to improve early response. It is known that not only is the number of extreme events increasing, but also the nature of extreme events there are more multiple extreme events in most food insecure countries, and the areas which are concerned by those is becoming larger. So early warning remains a very good investment as compared with dealing with the aftermath or with the damage of extreme events. And also with policies as those that have been already remembered, like the SDGs, but also the Green Deal, which has been recently proposed by the European Commission. We need both early warning and we need agricultural monitoring to be able to monitor the impact of such policies. So these are the needs, while on the other side we also have opportunities. We have seen in these presentations what can be done with Sentinel-1, Sentinel-2, Sentinel-3 imagery, for example, for in the field of water use efficiency. But there is really tremendous opportunities also for using these data together with new technologies, with new methodologies in the areas of big data processing, machine learning, cloud computing. And combining these two, we can really progress in the generation of indicators, as we have seen, but also in making available platforms for agricultural monitoring and early warning. In this presentation, I would like to look a bit more in detail at a platform we have developed for agricultural production hotspots monitoring. It is mainly aiming at making available better evidence about drought and about coming up problems for agricultural production anywhere in the world. It is also an attempt to exploit in a coherent and continuous and timely way the global Earth observation and climate data which are available. And it is also, as I said, I think already, a way to go beyond maps and indicators to derive analyzed information that can be used by a broader user community, not only Earth observation scientists, but also agricultural analysts, food security analysts, and also policy analysts. The platform I'm going to present is made up of 3 integrated information platforms at different spatial resolutions and also targeting different users communities. So the first level is a global level that looks at countries nationally and identifies them as possible agricultural hotspots. This analysis is done every month for 80 countries which show a high risk of food insecurity. And the short narratives and this agricultural hotspots classification is really made or aims at an audience of decision makers and policy analysts and food security analysts. A second platform, which goes more into detail and zooms into province level or to the second subnational level. This is updated every 10 days. It's fully automatic, and it also shows all the indicators which are behind the drought warnings that we provide here with different colors. So all indicators can be visualized in a kind of web GIS, but also we can look at the history of the indicators over the last years. And so this is already more detailed, and it targets an audience of typically agricultural analysts who are interested in looking at agrometeorological indicators. And then we have a third information platform, which is the one that I would like to look mainly at today. This is really the one that exploits the latest generation satellite imagery at 10 meters resolution, so mainly Sentinel-2 and Sentinel-1. And this is really the one that allows to zoom in to the field level and to the farm level, and to look at field performance, to look at areas, at whether fields have been planted or not, but also at surface properties and change, such as flooding, burning, fires, clearing, etc. We get globally new Sentinel imagery every day, every 5 days, and in this platform, what you have in addition, or what is the added value to other platforms that you know, is that they can be accessed in a very easy way, basically visually, by just setting the parameters on the left side to visualize them quickly for any agricultural areas globally, and to compare them to previous years, or to do simple computations such as NDVI or NDVI differences, but also to show the full time series information by deriving profiles or showing image chips for a given field or a given farm. So let me show you a few examples. I just selected here a situation that doesn't look very nice, but in fact it isn't very nice, because it's an area in Kenya, south of Lake Baringo, that has been flooded now since May. So the dark blue areas are fields and other vegetation covered by water already for a long time. The farmers there have left, have abandoned the areas, because after 4 or 5 months of water on the field, it's really difficult to use them. The greenish areas on top are areas which are normally flooded, or let's say half of the years of the historical series. So you can see that this year is really exceptional. And if you compare it, for example, quickly with last year, you can see that most of the fields were not flooded, and also the natural vegetation in red was not flooded. By looking at the full time dimension of this, one can retrieve very interesting information for monitoring at the field or at the farm level. By looking, for example, at the image chips around a central point, you can see when the flooding started exactly and how it expanded every 5 days. And on top, you see NDVI profiles. The green one is the MODIS profile, but the one I think which is unique to this platform is the Sentinel-2 profile, the blue one. This is in near real time, is cloud filtered and smoothing by using the Whittaker algorithm. So it is really, I think, exceptional that we can interpret and look at high resolution time series NDVI profiles more or less in the same way as we are used to do for low and medium resolution profiles. You can see that the point in the middle of this image chip started to be flooded on July 15, and then continues to be covered by water since then. So I think this is really quite powerful information to go down, zoom at the field level, and understand what happens at the field level, what are the dynamics. In the tool, one can do much more, can draw polygons, measure the area, extract statistics for the area, and so on and so on. I'm not going into all of that, but I would rather like to show you some examples of how this has been used in the last years for major droughts and floods and other extreme events. So the idea is that one uses this ASA platform with its 3 different components that you have seen at different scales. In 2019, in February, for example, South Africa was defined as an agricultural production hotspot, because we realized, thanks to the Warning Explorer, that most of the most productive provinces were showing anomalies for both rainfall and biomass indicators. And with the high resolution platform, the one we have just seen, we were able to zoom in and to look, for example, inside Free State, which is one of the larger and main high potential agricultural areas in South Africa. We were able to identify specifically the farms and the areas which were not able to plant because of the drought. So if you look at this on the left side at the January-February image, it's a false color composite. So in green, you see mainly fields that had not been planted, while to the right, at the same time of 2018, the red fields, those are fields with active vegetation that have been planted with maize at the same time. The same thing can also easily be shown by using NDVI difference, which is all computed on the fly, so in a question of seconds when you use that platform. And from there, you can quickly see what is the anomaly as compared to the previous year. Because all this is done in the cloud, there is no need to download anything and to store it on your computer or to edit it in a GIS. Everything can be recreated on the fly by just using the link. Another example, because we have looked before at Syria, it was said that Syria, of course, has big problems of agricultural production since the conflict began during all the conflict years, which led to an erosion of irrigation infrastructure and to generally lower production. That's absolutely true, but on top of that, still there's a large interannual variability. So, for example, in 2018, in April, with the ASAP system, we had a number of provinces of Syria flagged as agricultural drought areas. And again, if you zoom in, this is what the area, for example, in Hasakeh province, around Hasakeh town, looks in a normal year. This is April 2019. You can see the red fields are all nice and active at this time of the year. And also you can see 3 dams which are filled up with water. Now, if we look at the same area in 2018, April, with Sentinel-2 images, this is what it looked like. So only less than 10% of the fields were cropped due to a combination of course, of the irrigation infrastructure problem, but more than that, in that year, it was really the lack of irrigation water. So it is really possible with this imagery to quickly zoom down to single fields and have an idea of what's on the field, whether there is active crops or it's covered by water for either irrigation or because of floods. The Sentinel-2 images are very powerful and are great data for that. But it is also true that during the crop season, very often it is raining a lot and areas are cloudy. So Sentinel-2 imagery cannot be used during the whole crop cycle. This has become very clear, for example, during a major recent extreme event, the cyclone Idai that hit part of Mozambique in March 2019. We tried during the event and in the aftermath to map the flooded areas with Sentinel-2, but you can see with the difficulties we encountered, both in 2019 and looking at the same time in 2018, there were many clouds, so we could not do good flood extent maps with Sentinel-2. This is why in the system we also use Sentinel-1 composites, and we could easily map the flooded areas which appear here in this greenish bluish color, and were not there at the same time of the previous year. For Sentinel-1, we can also retrieve time series profiles of the backscattering coefficient, and that allows, for example, here to visualize the dates when the rainfall, exceptional rainfall, and the flooding started, and the backscatter goes down. And again, we can see in the image chip time series the context around the point we are looking at, and there as well we can see the water very, very easily. 2 minutes, please. Yeah, I'm closing. So the system is also used not only for drought monitoring and floods and agricultural monitoring, but it also shows land use changes. That is very useful, for example, in looking at the transition from forest to agriculture. This is a case in Uganda where we're looking at in real time at deforestation in the Bugoma forest. So you can see at the beginning of August, this area was still closed forest. While zooming in a little bit, at the beginning of September, this is an area where there's a sugarcane concession has been given to a company, and we are monitoring every 5 days how the clearing goes on, how the new roads are built, and then once we have quickly monitored that in the ASAP high resolution viewer, we can also make more detailed maps that then inform the EC delegation and the Ministry of Environment in Uganda. So we continue working on this system. As we have seen the examples with the Warning Explorer, at the moment go down to the first subnational level administrative areas like provinces. We are now extending it to the second subnational level. We are adding more meteorological forecasts. At the moment, there are 10 daily CHIPS and ECMWF forecast, rainfall forecast data, but we are also working on integrating seasonal forecasts. We are working on using machine learning for national level yield forecasts. I think that is also, you have seen many other attempts in the other, references in the other presentation to yield forecast with satellite data. And we are improving another few points. For example, the Sentinel-1 data visualization in the high resolution viewer. We are also discussing with several parties to make customized copies or clones of the whole system, for example, with ICPAC for the IGAD region in East Africa. So overall, I would say that this platform efficiently provides timely multi-scale information for agricultural monitoring. It is a user-friendly modern platform that really enlarges the user community of satellite imagery from the scientists and the programmers to non-Earth observation experts. Everything is documented and there is information, is free and open. And it has been developed by quite a small team. And we are, of course, always dreaming of expanding it and continuing the development with more resources. Thank you very much for listening and for the attention. And with that, I would like to give the floor back to the chairs. Okay, thank you very much, Felix. Let's see if there are some questions for Felix. At the moment, I don't see anything, but maybe that's coming in. So to start with, I would like to ask a question then, and that is, since this system it can zoom in at such a high resolution, it will be also can also become useful for farmers themselves. So did you think, or maybe it's already in practice, of using it for advisory services to farmers? Thank you. It's a good question. In our situation at the Joint Research Center, our main use is not really to work directly with the farmers, because our main role is really to inform the policy colleagues in Brussels in the first place. So we are usually working either with people who do monitoring at the country level or at the global level. But it's certainly one of the possible uses, and I think it will be interesting for us to work on this with partners who are, let's say, between our level and between the farmers, and can use the system to derive climate services, for example, and make them available to farmers. Mm-hmm. Thanks. Mm-hmm. Okay, thank you very much. Then now there are a couple of questions. The first question is from Joanne. And she asks, what is your confidence in the data information produced from the system? Yeah, that is difficult to answer without knowing exactly to what indicator or to what part of the system she refers. Of course, it really depends on the indicator, because we have some simple indicators that are used in a qualitative way, but we also have quantitative or model indicators, such as, for example, the soil, for example, the water satisfaction requirement index that we calculate at the global scale, and that we have recently validated in 2 African countries against biomass production data. We have found results that are comparable to the NDVI as a proxy still for biomass. So for that, we have a high level of confidence, but it really depends about what she refers to.
Mm-hmm. Okay, there are some more questions, but we can also open the floor for questions for the other presenters.
So I would like to go back quickly to Rados, because there were two questions that he did not respond to. He could not respond to, and the first question is which water vegetation index do you use, and did you validate with field data? That's one question, and the other question is from eLeaf, and that is on the scalability of the data fusion approach. If you can say something about that, Rado.
Yes, thank you for the questions. Well, regarding the first question, I'm not sure if it refers to optical water vegetation indices or not. So for optical water vegetation indices, we don't use any. What we do is derive the indices based on potential and actual evapotranspiration. And in there we have two kinds of indices, let's say. One is normalized, and the other one is the absolute values. The absolute values is basically potential minus the actual, which tells you how much extra water would be needed on a particular field to make the plants transpire the potential rate. And the normalized one goes between 0 and 1. And those indices have not been validated because this is more of a subjective thing. It's not something that can be really measured in the field with flux towers. This is more to the experience of the farmer, if he finds those maps useful or not useful, is he watering the same way or not. And we are working with a number of farmers and clients to trying to get the qualitative assessment of those maps. And the second question was about larger scale processing. So basically when it comes, well, the data fusion works on a pair of images. So you have one Sentinel-2 image and one Sentinel-3 image. So when it comes to time series, there's no problem at all, as long as you have the data from those two sources. You just match them up and input them into the algorithm and get the high resolution representation of the LST. For larger area as well, there is no problem. You just need to take care about, the tiles of Sentinel-2. There might be some artifacts on the borders. You might get multiple Sentinel-3 swaps for one Sentinel-2 tile from, for example, Sentinel-3A and Sentinel-3B. So there are some things that have to be handled there, but there is no there's no blocking point why you could not use the sharpening on a larger area.
Okay, thank you very much. Then there was also another question from Mark Noord to Nadja, who says, thank you for the presentation. And do you take the type of soils into account in your study area? Because there is a lot of heavy clay over there.
Yeah, so in the principal component analysis, what we're working on, we have this information on soil type and also the percentage of clay in the topsoil. So that is considered.
Okay, thank you. Then let's go back to Felix with a question from Roel van Holst. And he asks, thanks, Felix. How does the system analysts account for crop rotation in the inter-annual comparison analysis of vegetation indices at field level?
Yeah, thanks, Roel, for the question. It's an important question. In the first two platforms, so in the early warning explorer and in the ASAP assessments, we are not able to take that into account. So we only use an average crop mask and an average yearly phenology. But certainly we think that by using the high resolution viewer, if the interpreter or the analyst has some additional knowledge, then he might be able to use the information that he gets from the satellite imagery also to interpret together with the knowledge he has to know what crop is on the field. So the system is not automatically taking it into account, but I think there is some way around it with the higher resolution.
Okay. Thank you. I stay with you, Felix, because there is also a question from Martin Calveri, and he says, thanks Felix for the presentation of these useful tools. For the high resolution viewer, which cloud masks did you use? Many clouds are omitted. Data is TOA or TOC?
Oh, great. That's an excellent technical question.
Yeah.
In fact, for the mapping, we don't use any cloud mask. So if you go to the system, you will notice that the data is TOA, and the maps are basically showing the Sentinel-2 imagery together with the clouds. That's something that one has really to take into account. For example, when deriving an NDVI difference, part of the difference is, of course, influenced by the cloud. So the user really has to decide which part of the scene is of good quality enough to compute a meaningful NDVI difference. But on the other side, in the profiles, there we do some cloud screening, and then also we apply the Whittaker smoothing. So the profiles are to some extent getting rid of the cloud problem. So they are not cloud filtered, the profiles are. Thanks.
Okay, thank you. Now there is a question from Nora Yali. I don't know if I pronounced this properly, and I don't know if it is still for Felix or not, but it can also be for everybody. The question is, are you using any kind of ground truth data besides satellite data monitoring? Is anybody who wants to say something about that? It's very quiet now.
I think this question will be directed to Felix. Again, maybe looking at the time.
Okay. Felix, then you can answer maybe.
Okay, thank you, Nora, for the question. We are using ground truth data for validating some of the indicators and some of the reference data, such as, for example, the agriculture mask that we use, or the phenology model that we use behind the system. But I think you referred to the high resolution maps. So, for example, it is true that when we look at flooded areas, I mean, this is there is of course quite some uncertainty between what is really flooded and by how much water, and what is not flooded. That is not immediately obvious by just looking at the Sentinel-2 top of the atmosphere reflectance. So at that level, we are not using ground data, and to produce a real flood extent map, one would definitely need to. So we propose this environment as a quick monitoring tool for rapid interpretation, but we don't propose it for deriving quantitative flood extent maps.
Okay. Thank you very much. The next question is definitely for everybody, I would say, and it comes from Wouter. So I think Wouter can ask it himself, please.
Sorry, my question is related to the use of the Sentinel data. I was wondering where you get the data from. So that really applies to all presentations I've seen today. So do you get it, from which data distribution portal do you get it? Because I know that for accessibility issues, some people even use a Google Earth engine, which is probably not what ESA or the Commission would like to see. But so I'm very curious about that.
I can maybe answer.
Okay, go ahead, Rhoda.
Yes. So in the Sanity plugin, the data is retrieved directly from Sci-Hub. When we do, larger scale processing, you're right that Sci-Hub is quite slow, and now as well, there are the problems that the long-term archive has been activated. So data older than a year is not directly available online, but you have to order it and wait, and you can only order limited number of products at a time. So in that case, we usually go to Amazon if we want to have the data in the actual safe format. If we don't need the data in safe format, we also sometimes use Google Earth Engine for large-scale processing. So it kind of depends on the use case. But yeah, I agree there are limitations to the official distribution for Sci-Hub.
Mm-hmm. And we're moving to the next. Who was that? Nadja, where does VanderSat get the data from?
Yeah, I think I was actually now checking where did we get our data from, because this is I think 1.5 years ago that I did that. But I think we also use this Sci-Hub ingestion, but it was a very, I remember that it is and it still is a struggle to have a good flowing ingestion system. But also with, of course, the whole atmospheric processing part. Yeah. So yeah, there is definitely always space for assistance there.
Well, in that respect, the work shown by Felix is also very important, I guess, that you have easy access to the data. Actually, I have... Okay. So actually, I have a question also related to Felix, because so accessibility is what I experience as a data provider in different domain. And what I experience is that there are a lot of users struggling with getting access to the data. And scientific users, that's obviously often fine. They go to a portal, they can download the data, they can read .NET files. But particularly for the end users, you're targeting more or less end users. Felix, correct me if I'm wrong. You're providing access. But still, my question would be, do these users then know how to use the data? So do they know how to interpret false color image and then the BI index and so on?
Yeah, it's a very tricky question, Wouter. Thank you for that one. I would say in these 3 years that we have been making available the high resolution viewer to the open public, in most cases the questions we receive or the people that come back to us, they tend to use the data in the right way. I mean, we have also seen situations where that was not the case, but I must say I have rarely seen situations where somebody takes the data and uses them straight away without knowing what they mean. So in most cases, the users either look at the documentation which is available. So you, of course, what the answer to your question depends also on the quality of the documentation that you make available, or they come back to you with their questions and ask directly, is this right? I mean, is this interpretation I would give to this image, is that correct? Is the red actually vegetation or is that bare soil? So these questions, of course, they come back to you with, and you have to be ready to provide some assistance to continue to support the user. But in general, I have not had any terrible experience where, I don't know, a map from the high resolution viewer has ended up on a newspaper or somewhere else with a completely wrong interpretation. That has not happened yet. It doesn't mean that it will never happen, but until now I'm satisfied with it.
Okay, thank you. We have still a couple of questions over here in the chat box. But I do not exactly know to who they are addressed. But for example, well, Weil Seif, he asks, would this then help in finding out the crop water requirements during plant lifetime or adjust it? Can we link it with crop yield? So the site went to harvest. I don't know who could say something about it. Livia, could you say something about this, maybe?
Yep, why not? Thank you. Yeah, I think this, I mean, based on the data we publish on WaPOR, there have been examples of applications. So I link it also back to the previous question. based on our experience, we realized that it is useful to have the data delivered, for example, through API, because in this way you can develop applications targeted towards the demands of the users. And this is what we've been doing in the past years, and we'll continue on doing. So understanding what the requirements of the users are in terms of information and how to package that, and then use the API access to the database to let's say, publish this information in the right context. So going back to the question, some of this information is also related to crop water requirements, because we have data on reference evapotranspiration, actual evapotranspiration. Then we can indeed say something on the dynamics of the crop water requirement. So then decide when to harvest. Then maybe, I don't know. That of course needs to have some knowledge of the context, and that's why again an application that is developed with farmers and agricultural research organizations in the country could work in that sense. Thank you.
Okay, then there are two questions are left which I want to put together. That is one is from Sosdito from Mozambique, and who asks, are you considering validating the system for regions or smallholder agriculture? And there is a question on, is there enough knowledge of farmers to understand these complex relations, soil, atmosphere, plant, water relations, and how to translate all these results to farmers? So these two questions I would ask Elisabeth, if she can say something about it, because she is definitely an expert in modeling and in combination with using remote sensing.
So the first question was about validating the system for regions. Is it right? Yeah. Yeah. What we have, what we like to do is coming more to a super regional global view. So there was some effort in validating the whole system in Zambia, for example. So this has been definitely done in the past. And the second question, I think is that this is always very. It is about the knowledge of farmers to understand the relation. I think it is very, very important that we speak a common language. The scientists, also the farmers, that we can understand each other and put good value out of our research. So I think the farmers do have good knowledge about how they have to manage their crops and how the system works. So I think, this is it is very complex.
Okay, thank you very much. The time is up now, I believe, so I think we should stop now. I would like to thank everybody for this very nice and interesting presentation, interesting session. So this session ends now, but still there is the virtual requirement booth that everybody can attend through the Brello platform. So with this, I would like to close and thank everybody once again. Goodbye.